Okay, number 7 is our logarithmic function, and again, there are plenty of different types of logarithmic functions, but the one that we care about in calculus the most is the natural logarithm, ln of x. And so to plot a couple of points here, if I start with x is equal to 1, that's going to be natural log of 1, which is equal to 0. So we're going to have the point 1, 0 on the graph. If I have e, that's going to give me natural log of e, and natural log of e is equal to 1. And e is about 2.718, so I'm not going to try to be super picky here on graphing decimals, but I just wanted to give you a basic idea. And then this graph has a vertical asymptote at x is equal to 0, and it rides up that asymptote, goes through that point right there, and looks something like that. Okay, so what is our domain? Well, the very first x-coordinate that this touches is almost 0, but it doesn't actually ever touch 0 because of the asymptote there, and so that's why the domain does not include 0. It's an open parentheses with a 0 and then to infinity. The range is going to be all real numbers, negative infinity to infinity. This graph does not have any symmetry. It does not have any boundedness. It does have a vertical asymptote at x is equal to 0. There are no points of discontinuity in this graph. The function is always increasing on its entire domain from 0 to infinity. It does not have any maximums or minimums. And finally, end behavior is going to look a little different from some of our other functions. We are going to have a limit as x goes to positive infinity. And as x goes to positive infinity, the y values here are increasing without bound, and so that limit is going to equal to infinity. And then on the left end, we are again approaching 0 from the right, just like that square root graph that we had earlier, and that limit is going to equal to negative infinity, since as you approach 0 from the left, the y values are decreasing without bound. Okay, parent function number 8 should be pretty familiar to you, the absolute value function. Y is equal to the absolute value of x. And so if we just try to plot some points, the absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. So you can kind of see that's going to be a linear function on that side. The absolute value of negative 1 is positive 1. The absolute value of negative 2 is positive 2. So there's this other piece on the other side that is also a linear equation. And so the absolute value function is really just two lines basically glued together. Okay, so what is our domain? Well, taking a look at the picture, that's all of the x values from left to right. That would be everything, negative infinity to infinity. The range is all of the y values. The very first y value is 0, and we actually are touching 0, which is why we include it with a bracket. This graph does have some symmetry. It is symmetric to the y-axis, which means that we call the function even. It is bounded below, as you can see from the range and from the graph, the fact that you can draw a horizontal line below the graph. There are no asymptotes on the absolute value function. It is not discontinuous at all. It can be drawn without picking up the pencil. And it is increasing and decreasing on different intervals. So we're going to say here that it's decreasing negative infinity to 0, and it's increasing from 0 to infinity. And that change from decreasing to increasing indicates that we do have a min at 0, 0. It is both a local min and an absolute min. So make sure that you're staying aware of those differences. For the end behavior, we've got two limits. The limit as x approaches infinity of the function f of x, that's going to equal infinity, since on the right side the y values increase without bound, and on the left side they also increase without bound, which means I'm going to have limit as x goes to negative infinity of f of x is equal to positive infinity. All right, for parent function number 9, we have what's called the greatest integer function. We don't mess with this function a ton, but here's the equation for you, and there's actually a couple of different ways to write this, but here's the way that I like: integer of x. You also sometimes hear this called the ceiling function, but here's how it works. Basically, you have, let's say, 0.7. well, what's the biggest integer? What would the next integer be? The next integer would be 1. Same thing for 0.4, that would also be 1. Same thing for 0.2, that would also be 1. If you had 1.1, the next integer up would be 2. And so what this graph ends up looking like is sort of like a step ladder, so to speak, or like just a step function is really kind of what we call it. And so you've got that piece, and then you also have this other one going in the other direction. And so this is sometimes called the step function as well. And that's essentially what it looks like. Now the domain is actually all real numbers. There's a bunch of points of discontinuity there, but you can plug any number into the greatest integer function and get back an output. It doesn't matter what you plug in, it would always tell you what the next highest integer is. The range is really strange because you've got all of these gaps in the range. So the range has all of these integer values, but it's missing all of the values in between. So we basically just say for the range, we'll just keep it simple here and just write in words all integers. There is symmetry to this graph. It sort of looks like it might be symmetric to the origin. Turns out it's not, and you can prove that by replacing x with negative x, and you'll see that you're not going to get the opposite of the greatest integer function. So there is no symmetry. There is no boundedness either. There are no asymptotes. This is sort of a really strange function. There are a bunch of discontinuities. In fact, we're just going to put that there are infinitely many. And where do they happen? They happen at all integers. And for bonus points, what type of discontinuity is it? They are all jump discontinuities. Okay, is this function increasing, decreasing? It's constant a lot of the times. Okay, I'm not going to be too concerned with the technicalities of what the answer to this question is, but we are going to say here that it is increasing in a sense, but it's also constant at some portions. I'm honestly going to just leave that blank and not worry about it too much. This is a function that we don't really pay that much attention to, but I think it's important for you to see it. Extrema. It turns out that by the definition of local maxes and mins, that all of these points are considered maxes and mins. And so at every integer you have a local max and min, which means here that I'm going to put that there are infinitely many and that they occur at all integers. Okay, and then what's the end behavior? Just real quick, the limit as x goes to infinity of the function f of x is going to equal to infinity, since as you increase x, the y value is also going to increase, and as you make the x coordinate more negative, the y coordinate is also going to be more negative, and the limit is going to be negative infinity. Okay, parent function 10 is called the logistic function. When you get to Calculus BC, if you end up taking that course, you'll actually study this a little bit more in depth, but I'm just going to give you a basic preview of it here. Here's the equation, y equals 1 over 1 plus e to the negative x. And so if we plot one point, let's just do that when x is equal to 0. That would be 1 over 1 plus e to the 0, which would equal to 1 over 2, and so we have a point at 0, 1/2. I'm actually going to change the scaling here so that up there is 1, and I'll put 1/2 right there. And then essentially what happens here is that we have two horizontal asymptotes. We have a horizontal asymptote at 0 and a horizontal asymptote at y equals 1. And the function starts at y equals 0. It grows up through that point and then sort of levels off once it gets to that other asymptote. And there's some really good real-world applications to this function. Okay, so what is its domain? Well, it touches all of the x values, so that would be negative infinity to infinity. Its range starts at 0 on the y-axis and goes up until 1. And I need to actually back up. It's not going to include 0 because it's an asymptote. And so this is going to be not including 0 until not including 1. Does it have any symmetry? Well, no, it doesn't. If it went through the origin, then it would, but it's not going through the origin, so it's not going to have any symmetry. Is it bounded? Yes, it is actually bounded in the true sense of the word, meaning it is bounded above and it is bounded below at the same time. Notice the two horizontal asymptotes. And so what are those horizontal asymptotes? They're y equals 0 and y is equal to 1. Discontinuity points, nope, we can draw that graph no problem without picking up our pencil. This function is always increasing or going up from negative infinity to infinity. It does not have any extrema, and its end behavior is very interesting because as you take the limit as x approaches negative infinity, and I think I did that out of order from what I've normally been doing, but this is the left end, that's going to be 0, and then the right end as x approaches positive infinity is going to equal to the y value of 1. Parent function 11 and 12, we are going to focus more in the spring on these, but I'm just going to give you a basic idea of what it looks like. So for our sine function, we write y is equal to sine of x. And the graph of this function starts at the origin. It then goes to a maximum point. It comes back to the x-axis, then to a minimum point, and then back to the x-axis. And it repeats this picture over and over and over and over in regular intervals, which we call periods. And again, we're not ready to get there just quite yet, but this is just a basic introduction. These maximum and minimum values occur at 1 and negative 1, so that's going to help us figure out our range. So the domain is going to be negative infinity to infinity, since as I mentioned, this graph just repeats itself in both directions. The range is going to be including negative 1 until 1. It actually does have some symmetry here. If you were to draw the other piece of it, it's going to have symmetry to the origin, which means that the sine function is odd. It is bounded above and below, and so you can just say bounded there. However, it doesn't have any asymptotes. There are no discontinuity points. Increasing and decreasing is really tough to answer here because you have infinitely many intervals of increase and decrease, and it's really tough to classify those, and so I'm not going to worry too much about increasing and decreasing here. There are also infinitely many extrema, and again, I'm not too worried about where they are at this point. We'll focus more on that in the second semester, as I mentioned. And the end behavior is sort of interesting here. This graph does what we call oscillates, and what that means is that there is no end behavior. It just keeps bouncing back and forth between negative 1 and positive 1, on and on and on and on and on. And so there's not really an end behavior to the graph, so really you can probably just put not applicable here for the sine function. Okay, finally the cosine function, very similar to the sine function in a lot of ways. Here's the equation, y equals cosine of x. This graph doesn't start at the origin, it actually starts at a maximum at 1, then goes to the x-axis, then to a minimum at negative 1, back to the x-axis, and finally finishes at a maximum point. And so you have something that looks like this, and there's our cosine graph. Again, this picture repeats itself over and over and over in both directions, and so that means our domain is negative infinity to infinity, and our range starts at negative 1 and stops at positive 1. There is some symmetry to this. If you were to keep going and keep graphing, it has symmetry to the y-axis, which means that the function is even. It is bounded, just like the sine curve. There are no asymptotes. There are no points of discontinuity. Increasing and decreasing, again, is pretty tough to write out in words or even in mathematical symbols, so I'm not going to worry about that here. There are infinitely many maxes and mins, or just extrema. Sorry for the bad handwriting there. And then end behavior, again, just like sine, sort of difficult to give in words. And so I'm just going to put not applicable there for end behavior.